Screen recording check. In back, we have system protection and reliability I wanted to talk to you guys today about. So, reliability is a measure of the system's availability from the perspective of the customer. So, for power to be available, what that means is that it's present at the service point, specifically the load side of the meter. That's where we consider power to have been delivered to. And it has to be suitable for use. So the voltage has to be present and stable and within an acceptable boundary, not too low, not too high, but within the delivery service standard. Now, when we don't meet that requirement, either because we have no power to deliver because there was an upstream failure, or because we've suffered damage to our system, or we're doing maintenance and have to intentionally put a customer out of power, that power is not available. And so we start tracking those hours. There's a regulator, the Ontario Energy Board here in Ontario, and they require us to track customer hours of outage. And they have us use a metric. We track on 3 different criteria. So we have our SAIDI metric, which is the number of hours of outage in a year that the average customer sustains. Now, a couple interesting things about that. From a SAIDI perspective, a connection is a connection. So you could have the hospital or town hall or a large factory, and they're given as much weight as an individual residential customer. A connection is a connection for all of these indexes. So it doesn't really track sort of the impact of that outage, because certainly I'd expect that, if Joe Average's house loses power, during the day, that's going to be on a Monday when he's at work. That's going to be a lot less impactful than, if an auto plant or a hospital loses power. But it is what it is. And so we track the average customer behavior over a year. And so we have 3 metrics. We've got our SAIDI, which is a duration index. Our SAIFI, which is a frequency index. And both of these are for sustained outages, where a sustained outage is greater than 60 seconds. If the outage is less than that, we don't consider it an outage, we consider it a momentary interruption. And we do track how many momentaries there are, although the utility is not held to an account for having a large number of momentaries. And in fact, one of our objectives in this course is to try and figure out how we can convert an outage that was going to be permanent and resulting in a truck roll and a lot of investigation, and turn it into a temporary fault that resolves itself. And so we have a momentary out tracking as well here, which is less than 60 seconds. So how do we go about maintaining availability? Well, we're going to tackle this from a number of different sides. First off, we want our engineering team. Everything starts in engineering. Before anything's built, it's envisioned by these guys. And so we want them working on a resilient design, right? So we want to make sure that when they're specifying, how big a pole, do we need a class 1 or a class 3, which is a measure of the pole's diameter and taper? Are they putting in a pole that's big enough and strong enough without being so big and so strong that it's expensive for no gain, and heavy and difficult to deal with for no gain? So, are they using appropriate tensions so that we can withstand extreme weather conditions? Are we guying properly? If we get an ice storm, is it going to hold up? And then the other thing that we want them doing is that, we want them to design things in loops, right? So there's some resiliency. If we have our source here and we have our customer here, it'd be really, really nice if we had another circuit that looked kind of like this, and now there's this tie point right here where if we have an outage here, instead we got some equipment that's out of service now, so we can't feed this way anymore. Instead, we can restore the customer using an alternate feed route. So we build loops into our system so that if we have failures, we have another path that we can follow. So another thing that we want to do is we want to design segmentation into our system. So if we have 5,000 customers fed off of one 27 kV feeder, which is possible, you certainly don't want a failure at the end of the line in a single phase subdivision to take out all 5,000 of your customers. What you want to do is you want to make sure that only the smallest number of customers possible experiences that outage. And if we get our protection design right, we get that segmentation built right in. All right, so if you were to visualize that, you can imagine if we've got our bus here, we've got, a tap off here, and that feeds out into a subdivision, and a tap, and that feeds out into a piece of subdivision, and a tap, and that feeds out into a subdivision. If we end up with a problem here, we want to segment things along this line right here, right? So that these customers go out of power here, but all these customers here have the power retained. And if we can do that, that makes troubleshooting things a lot easier too, because now we know exactly where to go. These guys are the ones without power, so we're going to head right here and start our troubleshooting in this little region instead of having to patrol the entire thing, which could stretch from one side of town all the way to the other. Another aspect we're going to work on is our protection design. So we talked last week about how arcs are hot and a tremendous amount of energy gets delivered into a fault, and this is going to utterly demolish our stuff if it goes unchecked. Having appropriate protections means that those protections are going to act to interrupt those faults and interrupt and extinguish those arcs before they have a chance to deal significant damage to our expensive equipment. All right, fuse links are cheap and we want them to blow. Transformers are more expensive. We don't want them to go. Some automated pieces of switchgear could be $50,000, $60,000, $80,000. We certainly don't want that damaged if we can protect it with an inexpensive fuse link. Maintenance is important. We gotta make sure that we keep up on our tree trimming. If your trees are cut well back, they tend not to end up in your lines. If you haven't done maintenance in 10 years, those trees are all grown in and they're interspersed with your lines. And I'm sure you guys have been driving and you've seen, a tree with a hydro line through it. That's not real good for reliability. You get a bad branch come down and all of a sudden your lines are all tangled up, or a strong wind and all of a sudden your lines are all tangled up. You've got a fault on your hands and it's a mess to clean up. So, keep up with our tree trimming and do our system inspections. We're obligated to inspect our entire system once every 3 years. In practice, that means you do 1/3 every year. If you see a cracked insulator as a utility, go deal with it. If you see damaged guy guards or damaged guys or missing U-guard or an arrestor that's starting to discolor, go and deal with it and keep up on your maintenance. It's not a lot different than maintaining your car, right? To get maximum value out of your car, you gotta change the oil. If you drive it till it quits and you've never changed the oil, you're not getting maximum value out of the thing. So same thing with our maintenance. You got to keep up on your maintenance. If you do, your stuff's going to last a lot longer. And then the last thing when we're talking about maintaining availability is the operational response. So are we being efficient in dispatching our emergency crews? And what about our technology? Are we using our technology to the best of our ability to make sure that before a line truck even rolls, the line maintainers know this is where the problem is at. So that they know, are they headed into an overhead section or an underground section of line? What sort of problems are they looking for? Was there bad weather in the area? So, what sort of technology can we use to tell the crew, this is where you need to go and this is the sort of problem. We found the fault only occurred on the red phase. You can tell that to someone. Now they know if there's a blue phase section of line, there's no point paying attention to that. That's not where the problem was. You can save time in diagnosing the problem and get the power back on faster. Makes everybody happier. So, we talked a little bit about how you maintain your availability. I wanted to talk a little bit more about the elements physically present in our distribution system involved in maintaining reliability. And so we talked about how anytime you have a switch and you're going to open that switch up, there's always going to be an arc involved. And so our switching elements in our system are we can break them up into three rough categories. And it depends, the categories are really based around how effectively they can deal with an arc. At the bottom of our priority, at the bottom of the list, we have assets that are not rated to break load at all. So you can't use these to break current, right? So a fuse holder, if you don't have a load bust tool with you, an inline switch, these tools have a non-load break rated elbow. These tools have no means to address the arc that is going to be drawn out. And so if you open one of these switches, you're creating an arc, and then that arc is going to be uncontrolled. And who knows where it's going to go or what it's going to get into. And if it finds its way over to another conductive surface, now you've got an arc established. And we saw in our video last week that was bad, right? And it's a self-inflicted wound, right? We did it to ourselves. So these classes of assets, they're really not designed to break load at all, right? So you have to break your load, and then you can switch, and then you can, you break load elsewhere with these. So they're still used for circuit segmentation, but they're not used for load breaking. Moving up, we get into our load break rated equipment. So this has overlap with our fault break rated equipment, but this includes stuff where the design is robust enough, the contacts are beefy enough, they've got some capabilities for dealing with an arc. They've either got some tool that's going to help snuff that arc or shunt it away or make sure that the arc is controlled, but only they have enough mechanical strength to overcome and pull the contacts apart quickly and effectively. But only enough strength and only enough arc snuffing capability to deal with normal operating currents, right? So maybe 300 or 600, or maybe if you've got a big one, maybe they've got 800 amps worth of load breaking capability. Right, so like a fuse holder with a load bust tool might be 200 amps worth of load breaking capability, whereas a very fancy automated piece of switchgear might be up to 800 amps of load breaking capability. So, in terms of your switching and doing your maintenance and working your restoration, these tools are great, but they aren't going to help you extinguish an arc under fault conditions. For those, we need a switch that's built even tougher. Something that's got a lot of resiliency and very, very strong actuation involved, so that it can break tens or 20,000 or more amps worth of fault current that are flowing through it. And for those, we tend to see that breaks down into three classes. We've either got breakers, and breakers always come with an associated relay. Later in the course, we'll dig into those a little more. A recloser, or a fuse. These are our three main classes that we're going to see that have the ability to not just interrupt a normal load, but interrupt a fault current. And they breakers and reclosers act in similar ways, and fuses are their own thing, and we'll be getting into fuses next. So it's easier to think about fuses as our fundamental protection element. So a fuse actually does two separate things for you. The first thing that it does is it makes a decision. Is the amount of current flowing right now okay? And the second thing that it will do for you is if it decides that the amount of current flowing right now is not okay, it will interrupt that flow of electricity. And it does that by melting. So that decision that it's going to make, so it does two things, and one of those decisions, it really does tend to change depending on how much current is flowing. So some decisions are going to have to be made really, really fast. Other decisions might be made really slowly. So if you get 5 times the full load rating flowing for a tenth of a second, that's not a big deal. Maybe we're starting a motor. That's fine. But, if we're at 5 times full load rating 20 seconds later, something's wrong with that motor. That motor's in the process of burning up. We got to interrupt the power. If you get a 10,000 amp fault flowing, you don't want to wait 20 seconds before you decide that that's an issue. You have to get that off right now. You want to act in the very first cycle. Or maybe if you have to wait, maybe you want to act over 2 electrical cycles. Now, an electrical cycle is only 16 milliseconds long. So you're talking about making a decision and then acting on that decision in a 100th of a second or 200ths of a second. So that's pretty quick. Now, if you're talking about overloading to, 150% rating, you might make a decision like that's not okay after 10 or 100, maybe even 900 seconds later. So fuses are operating at 2 really different time scales, and they're operating over some pretty wide ranges of fault current flowing through them as well. And so if we were to plot a fuse's behavior on a graph, we end up, it's not a very interesting thing to look at. If we take a look, this shows 2 fuses, the 25 and the 140 amp element, and you can see here, this is our 25 amp. There's 2 separate lines here showing 2 separate behaviors, and it looks like a vertical line, and then it makes this little tiny corner, and then it's like another horizontal line. And it's really hard to tell what is going on there. It doesn't give us a lot of insight. Very hard to tell the difference on the current difference here. And once the currents start going up, it's very hard to understand the time differences occurring here. So we need another way of representing our information. And what we're going to do is we're going to introduce a logarithm scale. So this is a different way of representing the exact same information. And if we do that, all of the sudden, we have the graph looks very different. This is the exact same lines that we saw here, but with a different scale. Now we can see it's very clear to us what sort of behavior we're looking at. We can make out the difference between these 2 lines all the way along. We see that there's actually a curved behavior here that persists all the way along instead of disappearing into a horizontal line, which is what it looked like we had on the other graph. So when we set up our axes this way, we're going to put time here. We're going to put current here at the bottom. And this forms a time current chart. And we're going to be using a lot of these for the rest of the class. So some features, we're going to have a logarithm scale on both our x and y axes. You may see values expressed in terms of scientific notation. So if you're rusty on your scientific notation, you might want to go and freshen up. All right, so we've got 10, 100, 1,000 amps, 10,000 amps, 100th of a second, a tenth of a second, 1 second, 10 seconds, 100 seconds, 1,000 seconds. So one of the another point of note, you'll never find a logarithm scale that crosses 0. You'll never find one that shows both a positive and a negative number. You can be negative, you can be positive, you'll never be both, and you'll never cross 0. Because as you can see, as we go down the line here, 1, a tenth, 100th, if we were to keep going down, we wouldn't hit 0, we'd hit 1,000th, and then 10,000th, and then 100,000th, and we'd keep going, as we kept going, our number would keep getting really, really, really small, but you'd never actually get all the way to 0. It's a function of logarithms, which means we'll never cross 0, but it also makes it really interesting, really useful for looking at numbers with a really wide range of behavior. So if we take a look at our logarithm scale here, there's some features I want to point out. Oops. And the first thing I want to point out is that each of these blocks occupies the same amount of space. So we're going to give the same amount of screen real estate, right? So right now we're doing 1, 2, 3, 4, 5, 6. So we get 7 dots worth of screen height here to go between 0.01 seconds and 0.1 seconds. So as we give to go, we're going to have the same 7 dots to go from 100 seconds to 1,000 seconds. So instead of breaking up our screen space based on a fixed count, we're going to have this dynamic counting occur. So for every place value, we're going to give it the same amount of space. All right, so from a 100th to a 10th gets the space. From a 10th to 1 gets the same amount of space. The next place value, from 1 to 10, same amount of space. Next place value, 10 to 100, same amount of space. So the other thing that this does is this changes our counting. So we're always going to be counting, and this is unique to logarithms, scales, is we always count by the last major division. So what does that mean? If we come in here and we zoom in, that means that here we're at 0.1, which makes this 0.2, 0.3, 0.4. So our last major division we had go by, 0.1. So we're going to count by 0.1, 2, 3, 4. We keep going. And you see the spacing in between the divisions is uneven. And this is another feature of our logarithm scales. So the distance between 0.8 and 0.9 compared to the distance between 0.1 and 0.2. Now, as we move up from a tenth, 0.7, 0.8, 0.9, 1, we're at 1. Now we're going to move up, and now we're not going to count by tenths anymore because our last major division was 1. So now we're going to count 2, 3, 4, 5, 6, 7, 8, 9, 10. We just hit 10. Our last major division was 10, so now we're going to count by tenths. 20, 30, 40, 50. Out to 100. When we're at hundreds, we'll count by hundreds. And onwards. So, getting this part straight is the secret to being able to read logarithm scales. If you can get this done, you guys are going to be cruising as far as reading log scales go. I'd encourage you to practice this. It is going to be with us for the balance of the class. So let's get going taking a look at some examples of plotting log graphs. Now, before we do that, there is one thing I'd like to point out, and that is that when we're taking a look at our log graphs and our scales, the 5 position isn't really in the middle. It's been pushed up. And we have to account for that. So if we go here to here, our middle position is about here. So if we were to divide this into quarters, it would look something like this. And you see that your 50% position is really a lot closer to your 3. And your 75% position is a lot closer to your 6. And your 25% position, right, your 2 is almost where you'd expect your 30% position to be. So if you have to do any interpolating, right, like if I ask you to find me 15 on this graph, 15 should be about here. Just under the 75% position. But certainly well above the halfway marker. So, let's get on to some examples. So let's start out with 2,000 amps for 1/10 of a second. So we're going to start out looking at amps. 10 to the 3, this is our 1,000, so we're going to count by thousands. 1,000, 2,000. So this is our vertical line that we're looking at, and we wanted 1/10 of a second. 0.1 is 1/10. So we can plot our point here. I guess if we can zoom in, we might as well plot our point right on. No, that's about as narrow as that pen wants to get. So let's make that 2,000. So what if we get, let's do 2,500 for 7 seconds. So we're going to go 7 seconds. So we're between 1 and 10. So that's 1, 2, 3, 4, 5, 6, 7. So we're going to be following 2, 3, 4, 5, 6, 7. So we're going to be following that line right there. And 2,500 amps. Coming over here, we have 1,000. So we're going to be 2,000, 3,000. So we're in this spot right here. So we're going to be somewhere in this region here. So if we zoom in, so we're zoomed in, so we had 10, 9, 8, 7. So it's on this line. We'll get our eraser going and tidy this up now that we don't need it anymore to keep our bearings. And this is our 2,000 and our 3,000 marker. So we know that our 0.5 is positioned over further than our 50% marker. So we're going to call it right there. Another example, let's do 15,000 amps for 3/100ths of a second. That puts us here. That's 1/100th, 2/100ths, 3/100ths. This is going to be our line. And we are looking for 15,000 amps. We have 10,000 amps, 20,000 amps. So we know we're between 10 and 20,000 amps at the 0.3/100ths of a second line, which we had identified. Better not use commas there, it could be confusing. And let's try another one. Let's do 33 amps for 450 seconds. Those are 10 amps. So we're looking for 33 amps. So we can count 20, 30. So we're in between these two bars. And we're at 450 seconds. So we go 100, 200, 300, 400. We're going to be in this box right here. inside that box. We were looking for 450. So again, around that 70% marker. 33 amps, which is just under the 50% marker. Amps for 450 seconds. We can also do a few examples, and we can read off. We can do a little practice reading values off a graph. So here's a graph. We have two sets of fuse curves shown. Next week we're going to start talking about what these lines mean specifically in the different regions they divide our map into. But for now, let's just practice reading some values. For our 25T fuse, how many amps before it operates at 10 seconds? Find our 10-second marker, follow it over, and we'll work off the black line today. So we are between 10 and 100. So we zoom in here. If this is 100, it's 90, it's 80. So we're pressed up pretty close here. So we're going to say that's probably about 77. We can say that's 77 amps on the black line, and on the red line, we are between 80 and 90. That looks like it's somewhere around, oops, 86 amps. Answering another question, we could say, if our 25T speed fuse were to experience a fault of 5,000 amps, how long would it take to operate? Yeah, bad example. To, let's say 500 amps. For a 25T fuse were to experience a fault of 500 amps, how long would it take to operate? So we can start out at 100, 2, 3, 4, 500 amps. And we are at 1/10 of a second. Dividing things up, you see our black line crosses right around our 3/4 marker, which we saw maps onto about a 6. So this represents 0.2. So here we would be at 0.16 seconds. for the black line and for the red line. What, somewhere around 0.19 seconds. So if we took our 25t and our 140k, and we wanted to know how much time difference there would be if they were to both operate under fault conditions for 1000 amps. What we'd want to do is look at the two lines that were closest to each other. So the red line in the lower fuse and the black line on the upper. So our first point here, we're into the hundredths of a second block. So we're at 1/10, 0.09, 0.08, 7, 6, 5. Which means that our actual point is somewhere around 0.048, 0.049. Scroll up, you see our next point is right here, and that's very convenient for us. It works out just so that it's on the line. We can see we're in our tenths of a second bucket here. So we can get 10 or 1 second, 0.9, 0.8, 0.7. Get out our calculator. You can then run the question 0.7 minus 0.048, which represents the line on our graph right here. We get 0.652 seconds. We could also ask a question at 100 seconds. How many amps difference is there between the 25T and the 140K? And again, we're going to want to compare our closest lines. So we're going to want to solve this line right here. So for our 25T, we're in the block between 10 and 100. So we're counting by tens. 90, 80, 70, 60. So you can see we're about 25% of the way there. So we're going to call that 62 amps. Here we're in the block between 100 and 1000. So we're counting by 100s in this block. 200, 300, between 3 and 400. And we're pretty close to, I'll call it pretty close to halfway in between So we're going to call that not 350, but 330 amps. If we get our calculator out and running, we get 330 minus 62, and we end up with approximately 268 amps of difference in their operating positions between at 100 seconds.